Consider a continuous time linear time invariant system. St is the input, xt, yt is the output, and we know the relation between the input and output in the time domain. That is, yt is ht convolution xt. Okay, this is the relation in the time domain. What is the corresponding relation in the frequency domain? We can use the convolution property. Y of j omega is equal to h of j omega into, convolution in the time domain that corresponds to multiplication in the Fourier domain. So if we take Fourier transform on both sides, we'll get this expression. And I think we already discussed this when we discussed about the Fourier LTI system analysis using Fourier series representation. Okay, so this is, what is this called? H of j omega. I think I have already mentioned this frequency response of the system. It is called the frequency response of this LTI system, H of j omega. That is the Fourier transform of the impulse response of the linear time invariant system. That is called the frequency response of the system. And we can write this in terms of its magnitude and phase. This is H of j omega. That is, we can write it as magnitude of H of j omega into e to the power j phase angle H of j omega. Okay. In the polar form, this is a complex valued function of omega. So we can express it in the polar form as magnitude of H of j omega into e to the power j phase of H of j omega. And this is called the magnitude response. It is called the magnitude response of the system. And this is called the phase angle. This is mode of H of j omega. This is called the magnitude response of the system. And this is called this is called the phase response of the system. Okay. And in terms of this magnitude response and phase response, we can express the output, the spectrum means this is the Fourier transform of the output, that is called the spectrum of the output signal. So we can express the magnitude spectrum and this phase spectrum of the output signal in terms of this. We'll get this expression y of j omega magnitude. This is called the magnitude spectrum of the output signal. That is, this is the relation. And phase, we can, what is the relation between the phase of the input and the output signal in terms of this phase response of the system? This we can write it as h of j omega. That is the phase of the that phase response of the LTI system, plus that is the phase of the input spectrum, input signal. Okay. So this is the relation magnitude and the relation between the magnitude and phase of the input and the output signals. And this is generally called the gain of the system. Gain means it is, remember, it is not a constant function, it is a function of omega. That means different frequencies are amplified by different amounts. Okay, if it is a function of omega. So it is called the gain of the system, and this is called, because the effect, what is the effect in the output phase of the system, the phase of the output signal? This is the phase of the input signal. Can we say that this is shifted by this much amount? So this is generally called the phase shift. This is phase shift. Okay. This is gain magnitude h of j omega. Sometimes it is called the gain of the system, and this is called the phase shift. Okay. So we have already seen that if you know the impulse response of a linear time invariant system, we can completely characterize that system using the impulse response. For example, we can find the output corresponding to any input using this convolution integral for a discrete time system. And one more thing, the similar expressions exist for discrete time signal. I'm not going to explain all the derivations. If you consider a discrete time system, the corresponding relation is Hn, Xn, Yn. Only difference is that this is a discrete input and output signals are discrete time signals. So the relation is y of e to the power j omega is equal to h of e to the power j omega into x of e to the power j omega. Okay, so you'll get similar relation. Instead of h of j omega, it will be h of e to the power j omega. Okay, since they are similar, I am not going to explain both the things. I will explain only the continuous time LTI system. And whenever there is a difference, I will explain the that difference also. What is the difference in discrete time LTI system? Okay. So we can completely characterize an LTI system using its impulse response. If we know the impulse response of a system, we can find the output corresponding to any input signal, and we can not only the output, we can get more information. For example, we can know about the stability of the system. We can know whether it is a causal system or non-causal system, whether it is invertible. All these properties we can get from the impulse response of the system. Okay. Now, if you are given a linear time invariant system, if we know the impulse response, we can completely characterize that system. Now, how to find this impulse response of a system? What is the impulse response? What is impulse response of a system? Give delta t as the input, measure the output. That is the impulse. That is called the impulse response of the system. If you are given a system, how to find the impulse response of a system? Did I explain this? How to find the impulse response of RC circuit? Using your normal circuit analysis techniques. I think I have explained that. So some systems we can find the impulse response. Theoretically, we can find the impulse response. Particularly when the system is consists of RLC circuits, if it is an RLC circuit, we can theoretically find the impulse response using the normal circuit analysis techniques. And another important class of systems that the LTI system is the systems that are described by the linear constant coefficient differential equations. Okay, linear constant coefficient differential equation means the linear combination of this is the general form of a linear constant coefficient differential equation. This is the general form of a linear constant coefficient differential equation. Linear on the left hand side, we have the linear combination of derivatives of the output signal, and on the right hand side, it is the linear combination of the derivatives of the input signal. So systems governed by this linear constant coefficient differential equation, there is an easy way to find the impulse response. We can directly, without finding the impulse response and then taking the Fourier transform, we can directly find the frequency response of the system. Okay. If xt, if I consider an input signal xt, and let's say its Fourier transform is x of j omega. What is the Fourier transform of this? That is the differentiation property of Fourier transform. What is the differentiation property? It is j omega to the power k into x of j omega. Now, if you are giving xt as if you are giving xt as the input to a linear time invariant system, let's say yt is the output, and if yt Fourier transform is y of j omega, then we can use the same differentiation property d to the power k xt by yt by dt, that is j omega to the power k y of j omega, using the same differentiation property. Now, if we take Fourier transform on both sides of this equation, this differential equation, what will we get? Taking Fourier transform on both sides of this equation, differential equation, using the differentiation property, we will get this. Now, can we find h of j omega from this? What is h of j omega? What is the relation? H of j omega, y of j omega, and x of j omega. Y of j omega is equal to h of j omega into x of j omega. The spectrum of the input signal multiplied with the frequency response of the system, that is h of j omega. So the frequency response is, need to get an expression like this, 0 to m bk is the frequency response of the system. This is relation. So h of j omega is y of j omega divided by x of j omega. Okay. So then cross multiply these terms, you will get this expression. So here in the differential equation, we don't have to, if the system is described using with a differential, if it is governed by a differential linear constant differential equation, linear constant coefficient differential equation, we can directly find the frequency response of the system. We don't have to first find the impulse response and then take the Fourier transform to get the frequency response. We can directly find this one. And let us consider this example. What is the differential equation governing this this linear this LTI system? What is the differential equation? What is the current flowing through this capacitor? Is it C into dyt by dt? Is it the current flowing through this capacitor? That is the current flowing through the resistor. So R into C, RC into dy by dt is the, this is the current flow, this is the voltage across the resistor. So we can write it as yt plus this one, this is equal to xt. Is it the differential equation? Is it the, if we apply the KVL, will you get this? This is the differential equation. Now, if we find what is h of j omega here, using this, is it this? What is the impedance of this? If this is it this impedance? And this is R. Then you can apply the voltage division that this is the impedance of if you give Have you studied this in your circuit analysis course? Like if it is x of j omega, y of j omega, then it is y of j omega. You can apply the simple voltage division rule 1 upon j omega c by r plus 1 by j omega c into x of j omega, isn't it? So y of j omega divided by x of j omega is this. If you simplify this, you will get 1 upon j omega rc. Is it? So there are different methods to find the frequency response of the system. Okay. Okay, this is when we know the differential equation that governs the linear time of a given linear time invariant system. Then we can directly find the frequency response. And similar expression is there for discrete time system. In the case of a discrete time system, it is linear constant coefficient difference equation. Okay, difference equation. That is summation k0 to this is called a linear constant coefficient difference equation. Here in the left hand side, it is the linear combination of the delayed versions of the output signal yn, and here it is the linear combination of the delayed version of the input signal xn. So the relation, this is called a linear constant coefficient difference equation. And if you take the Fourier transform on both sides using the time shifting property of the Fourier transform, we'll get this expression 0 to m ak e to the power minus j omega k into y e to the power j omega. Take the Fourier transform on both sides. And if you cross multiply these terms, you will get this h of e to the power j omega. That is the frequency response of the discrete time system 0 to n bk. Then it is e to the power minus j omega k divided by that is how we find the frequency response of the system if we are given the difference equation.